So far we have discussed the concept of the metric space, various examples, and also the relation with others functions and structures, various definitions, concepts and so on. So, in the metric space we have started with a set X, an arbitrary set, and then picking up the 2 points we have introduced the concept of notion of the distance on it. But so we have not yet considered the relation between the distance, notion of the distance, and the addition or scalar multiplication between the points of the sets. Say if x and y are the 2 points, then one can add x plus y, and one can also multiply alpha dot x if the corresponding set is a structure like a vector space. So, once we replace the set x by a vector space, and then we introduce the notion of the distance as we have introduced earlier, then it does not give any relation between the algebraic structures, that is the addition and scalar multiplication, and the metric distance notion. So, we do not get a useful theory further. So, in order to have a useful metric space or a useful theory, we wanted to define a metric, concept of the metric or notion of the distance in a different way by introducing a new concept of norm on a class which we call it as a vector space, and then with the help of that norm we introduce the notion of the distance, and that way we are able to connect or give a relation between the addition of a scalar multiplication and the distance function, and that will give you a useful structure. So, today we will discuss what is the vector space first, and then how to introduce the concept of the distance with the help of norm on this vector space. Okay. So, let us see what is the vector space. Vector space, sometimes some authors we also call it as a linear space. Vector space or linear space is a set X. Vector space is a set X over the field or vector space over the field K. Here K we will take R or C. R means set of real number or C is the complex. So, a vector space over the field K is a non-empty set capital X of elements x, y and so on, which we call as vectors, together with the two operations with algebraic operations with two algebraic operations addition, which we call it as a vector addition, denoted by say this, and scalar multiplication denoted by this. So, with the two algebraic operations, one is vector addition, other one is the scalar multiplication, where the scalar is taken from the field K of this, which satisfies the following property, properties. The first property is, say we take V1, the set V with addition must be an abelian group. Abelian group. Abelian group we mean that is the following conditions are satisfied. If X is a vector elements belonging to V, Y is an element belonging to V, then if we combine these two elements by the operation addition, then a new vector so obtained must be the point of B. That is, we call it that addition a closure property. This property is called the closure property, or we say the addition is closed with or vector is closed with respect to addition. Then if x, y, z are the 3 points, then x, y and z are the any arbitrary 3 points of V, then the x plus y plus z, this will be equal to x plus y plus z, which is known as the associative property. Associative property. And third, there exist, this is fine for there exist an element theta, which we call it the null vector, null element, okay, or identity element for addition, or identity element for addition, such that x plus this null element is the same as this plus null element theta plus x must be x, and this is true for every x belonging to capital X. So, theta, which we denote as a null vectors or the identity element with respect to the operation addition, it satisfy this condition. Then D, corresponding to each vector x belonging to B, there must exist a vector minus of x which is also in V, such that when we add these two vectors, the total should come out to be the identity elements for addition, whether it is added towards the left or towards the right. So, this is the identity elements. Here we say identity element, here we say inverse exist. Then another property is the commutative property, x plus y is the same as y plus x for every x and y belonging to capital X. This is the commutative property with respect to commutative property with respect to addition. Now, if these 5 properties are satisfied, then we say the class V with respect to the operation addition is an abelian group. If only the first 4 properties are satisfied, then we say it is a non-abelian group, means commutative property does not hold good. So, that way we can say, in case if there is only one side property is true, for example, C. In case of C, if only one side is true, x plus theta equal to x, or in the second D also if there is only one side, then we say left identity, right identity, like this we define the left inverse or right inverse. The concept is correspondingly can be defined. Okay. So, first part is that the set V with respect to the addition must form an abelian group. Now, second one is V 2. With respect to scalar multiplication, it must be closed. So, closure property with respect to scalar multiplication. That is, if alpha is an element of K, X is an element of V, then alpha dot X, this should be an element of B. So, we say the V is closed with respect to scalar multiplication. Then another property in this say V 3, alpha beta are the two scalars in K, then alpha plus beta x is the same as alpha dot x plus beta dot x, alpha dot x and beta. And here also we can say V 4 1 dot x is x for every x belonging to V, this is for every x belonging to V 4. And then distributive properties, this is distributive, also V 5 we can say alpha dot x plus y is the same as alpha dot x plus alpha dot y. Now, if where x and y are the elements of V for any arbitrary element x and y in V. Now, if we look these two property V 3 and V 5, the V 3 here the scalars are added and then it is operated on x, but in case of this the vectors are added and then operated alpha is operated on x. So, basically you can say the scalar multiplication is distributed over vector addition. Okay. So, we can write like this. Then alpha beta dot x, that also an properties 6 alpha dot beta dot x. Okay. Yes, because this is alpha plus beta, this is the ordinary plus with respect to the scalar. Encircle is for the vector addition, okay, but this is not a ordinary, because what happens when vectors are given, say suppose I take a vector in 3-dimensional plane, then vectors will be, each vector will have a component, say a1, a2, a3, this is the vector. Okay. Now, when we add the two vectors x and y, b1, b2, b3, then basically we are taking x plus y, but when we add, then these a1, a2, a3, these are scalar, either it may be real or may be complex number. So, addition is done as per the real or complex rule. Say addition of the two real number is real, addition of two complex number is complex, and component wise we add. First coordinate is added with the first coordinate, second coordinate is added second coordinate, and like this. So, in case of the vector, that is why we require the vector field, because each vector, when we say vector, it has a component, and once it has a component, what are those elements, whether they are real number, they are complex number or anything else. So, those must belongs to a certain class, and that class called a field. Okay. Here in case of function analysis, we restrict our class either on the real line or maybe a complex plane, that is all. Okay. So, there are different type of operation. To distinguish these two, we have used the plus under the circle as the vector addition and dot within the circle as a scalar multiplication. Scalar multiplication, when a scalar is multiplied with a vector, then the operation dot within circle will be used. But if the two scalars are multiplied, then there is no need, there is no need, and we can just like here when you are taking alpha dot beta dot x, I will simply write alpha beta dot x. In B6 you see the difference, here alpha and beta are simply a real number. So, just a product is defined, ordinary multiplication, but here dot is used because x is a vector quantity. So, that is why it will be, and in the left hand side beta dot x will becomes a vector quantity. So, somewhere you will use the same dot product. So, that is why the difference must come out like this. Okay. Similarly, here in this case. So, these properties are satisfied, then we say if a vector v satisfying with this property. So, how many total properties are there? If you look, there are 5 properties here in V1 and another 5 here in there. So, total is 10 property. So, if a class V under the addition and scalar multiplication satisfy these 10 property, then we say V is a vector space over the field K, over the field K, and we write it this V over the field K with addition and scalar multiplication is a vector space. Okay. Sometimes we omit the field K. Once we identify or it is understanding that all the scalars are taken real, then we know the elements alpha beta, these are the reals. So, we do not write the VR, we simply say V, or K is a complex, we also say V. So, some author without writing the V K or some use the V within the bracket K, it means it is a overlay field K. Now, K may be real or K may be complex. If K is real R, then this is called the real vector space, is a real vector space. Okay. And if K is complex number, then this is called a complex vector space. So, real and complex vector space totally depends on the scalar on the field, what field you are using, okay, and that is clear. So, this gives you concept of it. Okay. Now, one more thing which I normally confusion is when we take 0 dot x, it means what is the meaning? 0 is the simply a real point, real number 0. When it multiply by a vector quantity x, then what you get? You get a vector 0 vector quantity or null vector or the identity elements with respect to the addition. So, these two should be different. Okay. That also one should keep in mind. Now, there are many examples of the vector spaces. The most simple and useful example is our say X, which is say R 3. Okay. R 3 means set of all elements vectors, elements are say x 1, x 2, x 3. Okay. Coordinates are x 1, x 2, x 3, where the xi's these are real number. So, set of all triples in the 3 dimensional plane. So, these are the vectors. Okay. Now, on this we are defining the addition and multiplication as follows. Dot as follows. If we take two vectors x plus y, then this will be equal to x means x 1 comma x 2 comma x 3 plus y means y 1 comma y 2 comma y 3, and the addition is done coordinate wise, and we are getting a vector x 1 plus y 1 comma x 2 plus y 2, x 3 plus y 3. Okay. Now, again x 1, x 2, x 3, by 1, by 2, by 3, these are all real numbers, where y is also real. So, x 1 plus y 1, x 2 plus y 2, x 3 will also be real number. Let it be this number, any number, I will say z 1, z 2, z 3. So, it is again an element of V. V means R 3, okay, because it is a vector in a 3-dimensional plane. So, if x is a vector in 3-dimensional plane, y is also vector. If we define the addition in this fashion, you are getting the new vector, which is again a point of R 3. And if we introduce the concept of dot, then alpha dot x is a real number. Okay. Let alpha be the real number, x be an elements of R 3, then what we get? Alpha dot x 1 comma x 2 comma x 3, and that will be equal to alpha x 1, alpha x 2, alpha x 3. So, this way we are defining. Okay. This is again a point of R 3. So, addition is, with respect to addition, R 3 is closed, with respect to scalar multiplication, R 3 is closed. So, basically the first and this property is satisfied. The first property A, the closure property with respect to addition is satisfied, then the property, closure property with respect to scalar multiplication is satisfied. So, whenever you introduce the addition in scalar multiplication, you must see that these two property must hold good, otherwise it will not form a vector space. Okay. So, these two things you should introduce in such a way, so that these two must be. Now, you can verify all these properties are satisfied. With these two operation, if you look, then what are the property? Let us say start with this. The first property is already true. The second property, associative property, if I look this one, x and y, this is our definition. Okay. X plus y is this one. So, suppose I take one more point z, then what happen this x plus y plus z, this will be. So, we claim R 3 with respect to this is a vector space. Okay. Why? Because the first property is true, V 1 A is true, V 2 A B, V 1 B. V 1 B is, if we take x plus y plus z, then what happens is this will be equal to, I am just writing x 1 plus y 1 plus z 1. Okay. Then simply x 2 plus y 2 plus z 2, and then x 3 plus y 3 plus z 3. Okay. Y 3 plus z 3, this is, and this will be same as where x is, let x is x 1 y 1 x 1 x 2 x 3, y is y 1 y 2 y 3, and z is z 1 z 2 z 3. Okay. So, if we introduce this, then what we get? Over the first bracket, x 1 y 1 z 1, these are the real numbers. So, real numbers satisfy the associative property. So, we can write x 1 plus y 1 plus z 1. Similarly, for the second, again these are real number, and real numbers are satisfying the associative property. So, we can interchange the position of the bracket, and we get x 3 plus y 3 plus z 3, and that is nothing but x plus y plus z. So, associative is satisfied. Okay. Then V 1 C V1C is there exists a null element or an identity element which satisfy this condition, x plus theta is theta plus x plus x. So, we claim if we take theta null element at 0 0 0 which is in R 3 and it satisfies the condition if we take x as x 1, x 2, x 3, then x plus theta is the same as x, okay, because it is nothing but x 1 plus 0, x 2 plus 0, x 3 plus 0, that will be the same as x 1, x 2, x 3, that is equal to x. Similarly, other way round also, okay, and V 1 D for corresponding to each x, for x which is x 1, x 2, x 3, we get minus x as minus x 1, minus x 2, minus x 3, such that x plus minus x, this is equal to null, because x 1 minus x 1 is 0 0 0. So, a vector is obtained, clear. So, we are getting this. Then E property V 1 E also satisfy, obviously you can verify x plus y is the same as y plus x. So, the property V 1, all the 5 property under V 1 are satisfied, therefore, it forms a abelian group, and then V 2 is already defined, it is belongs to V. So, it is satisfied. Now, B 3, if we look the V 3, you can see alpha plus beta dot x is alpha dot x plus beta dot x. I think this can be done. Okay. So, B 3, B 4 you can check it is satisfied, okay. And then B 5 and B 6. So, B 5 is alpha dot. So, V 2, V 3, V 4 check, okay. That is easy to check, Then we go for the B 5. B 5 says if alpha dot x plus y is equal to alpha dot x plus alpha dot y. So, let us take x as x 1, x 2, x 3, y 1, y 2, y 3. Then we take alpha dot x plus y, So, that is equal to same as alpha dot, what is x plus y? X 1 plus x 2, y 1, x 1 plus y 1, sorry, x 1 plus y 1, x 2 plus y 2, comma x 3 plus y 3, x 3 plus y 3, okay. That is alpha dot. Now, this multiply alpha multiply by this. So, x 1 plus y 1, comma alpha times x 2 plus y 2, comma alpha times x 3 plus y 3, and then it can be written as alpha x 1, comma alpha x 2, comma alpha x 3 plus alpha y 1, comma alpha y 2, comma alpha y 3. I just cut short the 2 steps. Okay. Then take alpha outside. So, it is alpha times of x plus alpha times of y. So, we can say the V 5 is satisfied. Similarly, V 6 can be proved. Okay. Clear? So, this forms it means in a 3-dimensional plane, if we consider the vectors, these are the vectors, collection of all such vectors, and then addition and scalar multiplication as defined earlier. So, it forms a vector space. So, since the elements are 3, elements of R 3 all the vectors and they satisfy all the 10 property of the vector space. Therefore, any structure X, any arbitrary set X with addition and scalar multiplication, if it satisfies those 10 property, we call it as a vector space. Why the vector word is used? Because as a particular case, when X is replaced by all 3, it satisfies those 10 properties. Clear? And since those are very standard notations, we call it as a vectors. So, that is why the correspondingly we say it is a vector. But it does not mean that always the elements of X must be a vectors. It does not mean. It may be anything, it may be sequences, it may be a functions, may be anything. Only thing we have to define suitably the two structure, addition and scalar multiplication. So, that all the 10 properties are satisfied. Okay. For example, if I take another problem which is say L2 space. L2 space. Okay. Now, what is L2 space? L2 is the set of those sequences xi1, xi2 and so on, infinite sequences, such that sigma of mod xi square is finite, is it not? L2 space, this is finite. So, when you are choosing these sequences L2, then find out the define the structure x plus y as xi1 plus eta 1, xi2 plus eta 2 and so on, where y means eta I belonging to L2, I is 1 to infinity. Okay. So, this and if we define the dot product as alpha xi1, alpha xi2 and so on, then we say they are all the elements of L2, closure property. And if we go just like a previous case, we will see that this L2 under these two operations forms a vector space. Okay, forms a vector space. Clear? Now, if these xi's are complex, then it is a complex vector space. If it is real, then it is a real vector. So, there is no need for modular sign if it is a real point. Okay. Then we have another one which is also interesting, the space CAB. CAB is the set of all functions x t which are defined on the closed interval a b and are continuous on it. So, set of all continuous function defined over the closed interval a b, okay, and are defined, well defined. So, CAB, let it be the set of all x, y and so on. Let us define the operation to addition and scalar multiplication as x plus y as, since these are the function at the point t. So, we define like this x t plus by t, x t plus by t. Okay. These are the functional values, okay, and this is the function. So, we are using the this plus sign for the functionals. We are like this, and then alpha dot x t we are defining as alpha into x t, alpha into x t. Okay. So, we are getting this alpha dot x t is alpha, where what is t? T is an interval belonging to a b, point in the interval a b. Okay. Now, if we look this definition, here these are the functions, x and y are functions just like f and g, and then combination of this defined over a t will give the values at the point t individually, and then addition is there. Okay. So, now with these two operation we will see it forms a vector space. Closure property is already satisfied. Why? If x is a continuous function, y is a continuous function, then x plus y must be a continuous function. Then any continuous function, constant times of the continuous function remains continuous. Okay. So, this is continuous. So, both the closure properties with respect to addition and scalar multiplication are satisfied. Okay. Then associative property holds, because the three functions are there, with respect to the plus they have a associative property, because these are all real numbers. This is the real valued function. You should write set of all real valued function, real valued, sorry, okay, set of all real valued functions defined, which are defined on AB and are continuous on this. So, this form. Now, what is the identity element for addition? What is the identity element for addition? Is there a continuous function which satisfies the x plus 0 equal to 0 plus x? So, in fact, a function which is identically 0, that is also continuous function. Constant functions are continuous. So, the function which is identically 0 will behave as a identity element. X is equal to theta for all t's, that is x t equal to 0 0. Okay. Clear? That is x t is equal to 0 for all t, then it is a identity function, and inverse is, if x is a function, then minus x t will be a inverse of this. So, all the properties are satisfied by this. Clear? Now, another is, say x is R n, all C n, they also form a vector space. What is R n C n? It is the n tuples where xi's are either real or complex. So, it is the extension of R 3, extension of C 3, and if we introduce the two operation as x plus y as xi 1 plus eta 1, xi 2 plus eta 2, xi n plus eta n, and alpha dot x equal to alpha xi 1, alpha xi 2, alpha xi n, then these are all belongs to R n or C n, and it forms a vector space. Okay. So, there are many examples of the vector spaces are available, where the elements are need not be a vectors, just like in case of the functions CAB, the elements are not vector at all, they are functions. So, we get that concept which is parallel to our vector. Okay. This one. Now, here we also require few more concepts like a subspace of a vector space. Vector space. A subspace of a vector space a subspace of a vector space X, which is vector space X, is a non-empty subset capital Y of X, non-empty subset capital Y of X, such that for all by 1 by 2 belonging to capital Y and all scalars alpha beta belonging to K, we have alpha y 1 plus beta by 2 must be a point of Y. Okay. What is the meaning of this? How to define the subspaces? The subspace is basically defined like this. Suppose we have a vector space V, where the operation, addition and scalar multiplications are defined. So, if we take any 2 point here, the addition of these 2 points are again here and scalar multiplication is also there. Now, y is a non-empty subset of V. Okay. The elements of y are also the elements of V, because it is a non-empty subset. So, if y with respect to addition and scalar multiplication is also a vector space, then we say y is a subspace of V. Okay. Clear? But in order to prove the y with the addition and scalar multiplication is subspace, you have to verify the 10 properties. Those 10 property can be avoided, simply you have to justify this condition. What condition is that if suppose y 1 and y 2 is a point in y, then if we take the linear combination of this y 1 by 2, that is alpha y 1 plus beta y 2, then that vector must be a point in y. Now, only this condition is enough. Suppose I take alpha and beta equal to 1 1, then basically the closure property is satisfied. If I take alpha to be 0, then scalar multiplication is closed. Okay. Similarly, if we take beta to be minus 1, alpha to be 0, it is a additive inverse for by 2, and all the properties can be derived. So, for a subspace, it is enough to show that if we picked up the 2 point y 1 and y 2, the linear combination alpha y 1 plus beta y 2 must be a point of y. Okay. That is form a vector subspace of this. Okay. Now, there are another concepts which we have now, the span of M. What is the linear combination? First, let us see linear combination definition. Combination. A linear combination, of a vectors x 1, x 2, x m of a vector space X is an expression of the form alpha 1 x 1 plus alpha 2 x 2. In fact, the dot product will be there. Okay. And here it this plus alpha 3 x 3 plus alpha m x m. An expression of this form alpha 1 x 1 and so on. Clear? This expression we call it as a linear combination. This gives a linear combination of x 1, x 2, x m. Now, here if we look that dot and square, it gives a very clumsy picture. So, what we do is we replace this encircle and dot with simply the thing just without writing anything, simply plus and dot. So, we can in simply way we can write alpha 1 x 1 plus alpha 2 x 2 plus alpha n x n, this expression. It is more attractive rather than to use this circle and plus, but the understanding is that between alpha and x 1 the scalar product is defined between these two vectors, because this is one vector, this is another vector, the addition is the vector addition. So, this is the understanding for this. Okay. So, henceforth we will use simply plus or dot without any circle. So, that okay. Then next is the span of M. For any non-empty subset, M of x, x is a vector space, okay, x which is a vector space, non-empty subset M of x, the set the set of all linear combination of vectors of M each called the span of M and denoted by and written as span of M. What is the meaning of this is, that is, if M is a set having the vector say x 1, x 2, x n, okay, M say, then what will be the span of M? The span of M will be of this type: alpha x I is 1 to n, that is alpha of x 1, alpha of x 2 and so on, or it may be of this type also: alpha x 1, beta x 2 and so on. Is it not? All may be of this type: alpha x 1, alpha beta x 2 and so on, and let it be say gamma x n, like this. Means you can pick up any elements of M, find the linear combination. It may be the one element, two element, three element, all n element at a time. So, m element at a time. So, all combinations, all possible linear combinations, the collection of this gives you the span, okay? And this collection span will form a vector space. Result is, the span of M is a vector subspace of X, where M is a subset of X. When M is a non-empty subset of X, the span of M will form a vector subspace under the same operation of the vector space X. So, it forms the vector, and we say by okay, span of a vector, and we say the this is generated by M. This subspace is generated by M, spanned by M or generated by M. We say is a subspace Y, and we say Y is spanned by M or generated by M. Okay? Clear? This was generated by. Then linearly dependent and independent. Linearly independent or linearly dependent vectors. Okay. A set of vectors x 1, x 2, x n or x r is set to be linearly independent if alpha 1 x 1 plus alpha 2 x 2 plus alpha n x n equal to 0 or theta 0 vector holds if all alphas are 0. Only if all alphas are 0. Holds only if, only you can use the word only also, if all alphas are 0. Then we say x 1, x 2, x n is a linearly independent vectors, otherwise linearly dependent. At least one of the alpha i's is different from 0, that is, at least one of alpha i's is not 0. then it is a linearly dependent vectors. Okay. So, it will be, for example, if we take say R 3 and find out the vector say x 1 as 1 0 0 or E 1, let it be E 1, E 2 as 0 1 0 and E 3 as 0 0 1. Okay. Now, these vectors E 1, E 2, E 3, these vectors are linearly independent. They form a linearly independent set. Why? Because if we take the alpha of some scalars alpha of E 1 plus alpha 1 plus alpha 2 E 2 plus alpha 3 E 3 is a vector 0, then it means it is of the form alpha 1 into 1 0 0, alpha 2 0 1 0, alpha 3 0 0 1, which must be equal to 0 0. So, that is the same as alpha 1 comma alpha 2 comma alpha 3 is 0 0 0. This implies alpha I is all 0 when I is 1 to 3. So, it is a linearly independent vectors. Okay. But if the vectors, if we take the vector like 1 2 3, say minus 2 minus 3 minus 4, okay, and minus 1 minus 1 minus 1. No, plus 1 plus 1 plus 1. Okay. Yeah. So, if we look these vectors, this set of vector is a linearly dependent vector. Why? Because if we multiply this 1 by 1 2 3, then again 1 by this, again 1 by this is 0, is it not? But alpha is are not 0. So, it is a linearly dependent vectors. Okay. So, in fact, any one of the vector can be expressed as a linear combination of the other two. If it is linearly dependent vectors, then one of the vector can be expressed as a linearly dependent vector of the other. So, I hope this is will give a sufficient hint, okay, and sufficient material for the vector space concept, which we will use in defining the norm. Okay. So, next class we will discuss what is the norm and how to introduce the metric. Thank you.